Alright, this is part 2 of Unit 5, and we are going to start with mole calculations. So this is a really big part of chemistry. It involves quite a bit of math, and so hopefully we can walk through these notes together, and then you'll have time to practice on Alex. And the learning objectives are listed here. So by the end of this part 2, you need to be able to convert between moles and particles, between moles and grams. You will learn how to use something called stoichiometry, and that will allow you to use a balanced equation to convert between grams of one substance in the equation to grams of another. We'll also go over how to calculate percent composition, determine the limiting reactant in an equation, and then lastly to calculate percent yield. So let's begin with an introduction of the mole. And so a mole is simply a quantity. It's an amount that contains a very large amount of items. And so we use the mole when we are talking about atoms because atoms are very small, and so we need a unit that allows us to measure an appreciable quantity of atoms. And so you see here that a mole is equal to 6.022 times 10 to the 23rd atoms. It can also be equivalent to that many molecules. And then here's an example using vitamin C. And so we see that 1 mole of vitamin C is equal to this number of molecules. And so the number that is represented here is called Avogadro's number. Avogadro's number. 6.022 times 10 to the 23rd. So we can use the mole and Avogadro's number as a conversion factor. And so when we are wanting to convert between one unit and another, we have to have what's called a conversion factor. And this allows us to relate the number of moles of a substance to the number of either atoms or molecules, whichever we are trying to change between, atoms or molecules. And so we see an example here. Above we saw that, for example, 1 mole of carbon is equal to Avogadro's number of atoms. And so that is the equivalent that we've written, and we can simply turn those into conversion factors by writing an equation, or a fraction, if you will, for this relationship. So we can either have 1 mole over 6.022 times 10 to the 23rd atoms, or we can flip this equation, or this fraction, and have the number of atoms on top and 1 mole on the bottom. And you see we can do the same for molecules. So this is what we call a conversion factor. And as we'll see in a moment, this conversion factor is going to allow us to change from one unit to another unit. So let's just jump in with an example. So this example comes from your textbook, problem 5.9, and it says how many molecules are contained in 5 moles of carbon dioxide. And so it's important to recognize what you're solving for. So we want the number of molecules. And it's also very important to recognize what you've been given. So we have 5 moles of carbon dioxide. So the first step is to identify what you're given and what you are being asked to find. And so I think it's helpful just to mark these in the problem themselves so that you know exactly what you were given and what you were asked to find. And so we see that our given quantity is 5 moles of CO2. And the quantity that we are being asked to find is the number of molecules of CO2. So we have a given quantity and we have our desired quantity. So step 2 then would be to write out our conversion factors. So again, we have to think about what is the relationship between moles and molecules. And if you remember, we said that 1 mole is equal to Avogadro's number of molecules. So this is the relationship, and now we want to write out the conversion factors. So we are going to turn this into a fraction, and so we can have 1 mole on top over 6.022 times 10 to the 23rd molecules. And unfortunately, there's no abbreviation for molecules. Or we could write it the other way, 6.022 times 10 to the 23rd molecules over 1 mole. So these are our 2 conversion factors that we can get from the relationship between mole and molecule. And so you want to choose the correct conversion factor that correct conversion factor should have your given amount on the bottom of the fraction. So the given amount needs to always be on the bottom. And the reason we do that is so that that unit will cancel. And so we can see in step 3, we have chosen the conversion factor that has our given unit on the bottom so that mole will cancel with mole. And then after we do our math, our remaining unit is molecule. And so that's the unit that we were trying to solve for. And so once you do the math, you see that you get 3.0 times 10 to the 24th molecules of CO2. So 5 moles of CO2 is equal to 3.0 times 10 to the 24th molecules of CO2. So this setup that we did using a conversion factor is a very simple way of converting between one unit and another unit. So as long as you know the relationship between the 2 units, then you can simply set up a problem that will allow you to cancel out the unit you were given and end with the unit that you desire. All right, let's talk about some other conversion factors. So there is something called formula weight. And this is the sum of the atomic weights of all the atoms in a compound reported in atomic mass units. And so that is the unit for formula weight. And so if we have a compound like iron sulfate, as you see here, the first step to finding the formula weight is to write the correct formula. And so this one's been written for us. You might be given the chemical name, and then you'll be asked to write the chemical formula. So the chemical name of this particular compound would be iron 2 sulfate. And so just make sure that you can go from a chemical name to a chemical formula and then vice versa. So in order to calculate the formula weight, we do need to have the chemical formula. Step 2 then is to multiply the number of atoms of each element by the atomic weight, and then you add up the results. And so this is how I like to go about setting up the problem. I write out my chemical formula, And then I draw this little arrow, and I want to count how many iron atoms I have. And so I see 1 here, and then my next element, my next capital letter, is an S, and I see there's 1 of those. And then my next capital letter is an O, and I see there are 4 of those. So I'm just using the subscripts to decide on how many of each of the different elements that I have. And then I would need to go to my periodic table and find out what the mass of each of these elements are. And so I'm then going to multiply the mass by how many of that atom I have, and that will give me the mass of that atom in the compound. And so iron, if you look at the periodic table, you'll find it has a mass of 55.58 AMU. And for sulfur, I have 32.06 AMU. And for oxygen, that would be 16. And since there's 4 of them, then that's going to equal 64 AMU. All right, and then I'm just going to take all of these numbers and add them together. So 55.58 plus 32.06 plus 64 gives me a formula weight of 151.91 AMU. So that is how to calculate the formula weight of an ionic compound. Next, we want to talk about molar mass. So the molar mass is the mass of 1 mole of any substance, and this is reported in the unit grams per mole. And so we write it like this: grams/mole. And so the value of the molar mass of a compound in grams per mole equals the value of its formula weight in AMU. And so we can simply look at a periodic table and find out the atomic mass from the periodic table, and that equals how many grams there are in 1 mole of that atom. So we see here, the example is carbon. Carbon has an atomic weight of 12 AMU. Carbon's molar mass is 12 grams per mole. So those are equal. And so if we know that carbon has a mass of 12.01 grams per mole, that means that there's 12.01 grams is equal to 1 mole for carbon. And for every element, it's different. But you can use the periodic table to help you find the molar mass of each compound. And so we can use the molar mass as a conversion factor. So it says the molar mass relates the number of moles to the number of grams of a substance. We saw that the unit was grams per mole. So it tells us how many grams there are in 1 mole. So in this way we can use molar mass as a conversion factor if we were wanting to convert between grams and moles. I wrote the wrong word. A conversion factor. All right, so let's practice this. The molar mass of water in H2O is 18.02 grams per mole. So we can use that fact and write 2 different conversion factors, just like we did before. So one of the conversion factors would look like this: 1 mole, 18.02 grams. Or we can flip that. We can put 18.02 grams over 1 mole. And so these are 2 conversion factors that we can write based on the molar mass. And so in our next problem, we are going to convert between grams and moles. So it says how many moles put a box around that, are present in 100 grams of aspirin. And aspirin has a formula of C9H8O4. And they were generous enough and gave us the molar mass of that aspirin, so we don't have to calculate that. But remember, we could calculate it very easily. We would just take, I'll write up here, we have C9H8O4. So we would take our carbon, and there's 9 of those. We have our hydrogen, and there's 8 of those. And we have our oxygen, and there's 4 of those. And then we would consult our periodic table and find the molar mass of just one of each of these elements and multiply it by the number. I put a O there, I meant to put a 4, sorry, times 16. And we would find all of this and add it all up, and we would get 180.02 grams per mole. So molar mass. All right, so in step 1, we would want to identify the given quantity and the desired quantity. So from the word problem, you want to always look for what's been given to you. So our given quantity is 100 grams of aspirin, C9H8O4. And the desired quantity is moles of C9H8O4. So let's stop here and talk just a moment about significant figures. We've had that lesson earlier on, but notice that our given quantity, 100, and then there is a decimal at the end. And that decimal is there to show us that there are 3 significant figures in this quantity that they have given us. And so that means that our answer, when we convert grams to moles, our answer should also have 3 significant figures. And so I like to just make myself a note of that as I am looking at my problem, so that when I get to my answer, I can make sure that I round correctly. All right, step 2, write out the conversion factors. So what is the relationship that we have between grams and moles of aspirin? So here the conversion factor that we are going to use is the molar mass. And it can always be written in 2 ways. And so we can either have 1 mole on top, and then the molar mass on the bottom, which was 180.02. Or we can put the grams on top, and then we put 1 mole on the bottom. So those are our 2 conversion factors. Now we want to choose the conversion factor that has our given quantity in the bottom of the fraction. So if we look back, our given quantity was grams, 100 grams. So we're going to choose the conversion factor that has grams in the bottom of the fraction. And we do that so that the grams can cancel. And so when we set up our problem, we always put what was given first, 100 grams of aspirin. Oh, I forgot to make, didn't I? The given unit in the denominator. I'm scrolling to see that formula, C9H8O4. C9H8O4. We were given 100 grams, and we're going to multiply that by the conversion factor that we chose, 1 mole over 180.02 grams. That was our molar mass for aspirin. And we set it up this way so that the units cancel. Gram cancels with gram. And we were asked to find moles, and that's the unit we have left. So then we would do the math, and we would round our answer to the 3 sig figs that we determined earlier. So 0.555 mole of aspirin, C9H8O4. So we set up this conversion so that we could change the unit from gram to mole, and this would be your final answer. So we can also use the molar mass to show the relationship between grams and the number of molecules, or even the number of atoms. So here we can see, we know the molar mass was 180.02 grams, and that was equal to 1 mole, and this was our aspirin, C9H8O4. This is also equal to 180.02 grams of C9H8O4 in Avogadro's number of molecules. Remember that 1 mole of molecule, or 1 mole is equal to Avogadro's number of molecules. So because of that relationship, we can set up this additional conversion factor. So sometimes that will come in handy. Let's look at our next problem where we can use that. So it wants to know how many molecules, that's where we're trying to find, are in a 325 milligram tablet of our aspirin. Just notice that some reason the molar mass has changed. Okay, we'll go with whatever it says here. All right, so the first step is identify the given and the desired quantities. So the given, we have 325 milligrams, and the desired quantity is molecules. All right, next we need to write out the conversion factors. And so since we were given milligrams, we do need to convert that to grams because we are going to use molar mass, and molar mass is in grams. And so to make that conversion, the relationship between milligram and gram is that there is 1,000 milligram is equal to 1 gram. And so again, we can write conversion factors, 1,000 milligrams over 1 gram, or we can put 1 gram over 1,000 milligrams. So we want to choose the correct conversion factor that allows us to cancel milligrams, which means milligrams needs to be on the bottom. So I would choose this conversion factor. Okay, then we need to look at how will we convert between grams and moles. Okay, so we can look at two conversion factors, and in fact a moment ago we saw that we could not only go from grams to moles, but we can use Avogadro's number and go directly to molecules. So let's do that, because we know that 1 gram is equal to, 1 mole is equal to Avogadro's number of molecules. And so here would be our conversion factors. We're going to use that molar mass, 180.02 grams, and we're going to put that over Avogadro's number of molecules. And then we can write it the other way. And we want to choose the conversion factor that will allow us to cancel grams. And so we see that this is the one that has grams on the bottom, so that's the one we're going to choose. And then the setup for the problem. You have your given amount, 325 milligrams. We have our first conversion factor that allows us to cancel milligrams so that we end up with grams. And then we have our second conversion factor which allows us to cancel grams and finally end with molecules. So our final answer here is 1.09 times 10 to the 21st molecules of aspirin. All right, so that was a little bit on converting between grams and moles and molecules. And so just remember to think about your conversion factors and choose the one that will allow you to cancel out the unit that you were given so that you could get the unit that you are being asked to solve for. All right, so we're going to move into using chemical equations to help us. So when you have a balanced chemical equation, a balanced chemical equation tells us the number of moles of each reactant that combined, and it also tells us the number of moles of each of the products that are formed. And so here we have a balanced equation, and we can see that we have 1 mole of nitrogen gas reacts with 1 mole of oxygen gas to produce 2 moles of nitrogen monoxide. Notice here they've written the coefficient of 1, but remember that when you're writing balanced equations, the 1 is understood, and you do not need to include that. And so we can use a balanced equation to make some more conversion factors. And so the coefficients in this balanced equation, remember those are the big numbers in front of each of the substances. The coefficients are used to form what are called mole ratios, relating moles of one thing to moles of another. And we can use mole ratios as conversion factors. All right, so when we look at this balanced equation, we can gain several conversion factors. If we wanted to relate nitrogen and oxygen gas, we would say that 1 mole of N2, oops, not sure what happened there, 1 mole of N2 over 1 mole of O2. And so that shows the relationship in this balanced equation between nitrogen gas and oxygen gas. And just as before, we could obviously flip that ratio or that fraction and put oxygen gas on top and nitrogen gas on the bottom. We can also relate nitrogen and nitrogen monoxide. And so the equation says that 1 mole of nitrogen gas is equal to 2 moles of nitrogen monoxide. And again, we could flip that. 2 moles of NO is equivalent to 1 mole of N2. And lastly, we could relate oxygen gas and NO, and the equation tells us 1 mole of O2 for every 2 moles of NO, and then we flip that. So as you can see, we have a number of conversion factors that we can use to solve lots of problems with this one balanced equation. So we see here that we can use the mole ratios from the coefficients in a balanced equation to convert between moles of one compound into moles of another compound within a balanced equation. So for simplicity's sake, we're just using the letters A and B. So we can convert between moles of A and moles of B, and we're going to use that mole-to-mole conversion factor that we just wrote out. All right, so let's look at a new equation and see if we can use our new skills here. So it says, using the balanced equation, how many moles, so this is what we're solving for, moles of CO, are produced from 3.5 moles of C2H6. So remember, step 1 is always to identify what you were given. So we were given 3.5 moles of C2H6. And what are we asked to find? We want moles of CO, carbon monoxide. And so when we look at the balanced equation, we can write out some conversion factors between C2H6 and carbon monoxide, since those are the two things that we are asked about. So, according to the balanced equation, for every 2 moles of C2H6, there are 4 moles of carbon monoxide, or we can write it the other way, 4CO over 2 C2H6. Again, we want to choose the correct one to cancel moles of C2H6 because that was our given quantity. And so we would choose the one that has that on the bottom. And so this would be our conversion factor. So you see they set up the problem. This is the given the given amount. We chose the conversion factor that allows us to cancel out mole of C2H6, sorry. And so then we do the math, 3.5 times 4 divided by 2 gives us an answer of 7.0 moles of CO. All right, let's move into our next part, how to convert moles of reactant to grams of product. So we're simply just going to add another step. Again, we're using a balanced equation. And this is just a little flow chart that you can use. We have moles of our reactant. We can call that moles A, like we did before. And first we're going to convert that to moles of B. And we're going to use the mole to mole ratio to do that, and we get that from the balanced equation. And then our second step, we're going to take the moles of B and we're going to convert it to the grams of B. And to do that, we're going to use the molar mass like we've done before. So we're simply combining the two things that we've just learned so that we can convert between moles of one thing to grams of another. All right, so step 1 is saying how many grams of O3 are formed from 9 moles of O2. So we've identified our given and our unknown. And our first step then would be to convert the number of moles of the reactant to the number of moles of the product. So we were given 9 moles of O2, which is our reactant, and we're asked to find how many grams of O3, which is our product. So we want to think about how can we convert between moles of O2 and moles of O3. And so we're going to use that mole ratio. So our balanced equation tells us 3 moles of O2 over 2 moles of O3. Or we could write the other conversion factor, putting moles of O3 on top and moles of O2 on the bottom. We want to take a look back at what we were given, and we were given moles of O2, so we want to choose the conversion factor that has moles of O2 on the bottom, so that would be this conversion factor. And then we will set up our problem. We'll put what we were given, 9 moles of O2. We're going to multiply that by our conversion factor that has O2 on the bottom so that moles of O2 cancel. And we're left with moles of O3. And so do the math, 9 times 2 divided by 3 gives us a total of 6 moles of O3. So that's the first step. Next, we need to convert the number of moles of product to the number of grams. So remember, it asks us for grams. And so we find the molar mass of O3, and that's simply taking 16, which is the mass of 1 mole, times 3, and that gives us 48 grams per mole. So we can use this as our conversion factor, 1 mole over 48 grams. Or we could do 48 grams over 1 mole. So we want to choose the conversion factor that allows us to cancel mole of O3. So we would want to choose the conversion factor that has mole of O3 on the bottom. And so that would be this conversion factor. Then we set up our problem. We're going to take the 6 moles that we solved for, 6 moles of O3, multiply it by the conversion factor that allows us to cancel moles of O3, and that gives us a final answer of 288 grams. We can look back and see that we need 2 significant figures, so that would round to 290 grams of O2, and that would be our final answer. Feel free to stop and pause, maybe rewind, watch again. When you get to the practice problems, you may want to come back and rewatch this so that you can get the hang of it. We're going to move on. The next part, converting grams of reactant to grams of product. So we're just going to add one more step, how to convert grams of reactant to grams of product. So here's the problem. Ethanol gives us a molar mass. Is synthesized by reacting ethylene with water. How many grams, that's what we're asked to solve for, are formed when we have 14 grams of ethylene. So we want grams of ethanol from 14 grams of ethylene. All right, so ethanol is here, and we were given 14 grams of ethylene, 14 grams. So this is what we're solving for in grams. Sometimes it helps just to write that out. This is a little flow chart that may help you. We're starting with grams of A. Our first step would find moles of A, and remember we're going to use molar mass to do that. And then we're going to go from moles of A to moles of B. And to do that, we're going to use mole-to-mole conversion factor. And lastly, we're going to go from moles of B to grams of B. And again, we're going to use the molar mass. All right, so they have set up the problem here. This is what we were initially given, 14 grams of C2H4. We're going to use the molar mass of C2H4, and notice that we have grams on bottom, and remember that so that grams cancels. Next step is to convert between moles of C2H4 to moles of C2H8O, and so we're using that mole to mole ratio, and in our balanced equation that's a 1-to-1 ratio, so we have it set up so that moles of C2H4 cancel. All right, and then we have moles of C2H8O. The next step would be to use the molar mass. We want to put moles on bottom so that moles cancel. And we finally end up with grams of C2H8O, which is our final answer. So as we put this in a calculator, just keep in mind that the less keystrokes you make on the calculator, the less likely you are to make a mistake. So as I'm working through this, I see 14 times 1 divided by 28.05. Well, there's really no reason to put in the 1 because I know what 14 times 1 is. So if I were entering this, I would say 14 divided by 28.05. And then I look at my next step, and it's multiplying by 1 and dividing by 1. Well, not only do the units cancel, but the 1's cancel. So we can skip that entire step because everything's canceled. And so then just skip on over to the last step. So it would then be times 46.07. So look for ways that you can decrease the number of keystrokes that you have to make on your calculator, and you're more likely to not make mistakes. And so that's always nice. All right, our next topic that we'll be learning is something called percent yield. And so percent yield is an equation that you can use to calculate basically how good a job you have done in the lab at recovering a certain amount of a substance. And this is often used in the lab. Sometimes this is an indicator of the grade that you get in the lab. So the higher the percent yield, the better. Probably will never get 100% yield because of human error and things like that. It's very difficult to get 100% yield, but the closer you can get to that, the better. And so we have this equation. It says that we take the actual yield over the theoretical yield. So let's look at those two words. So we have the theoretical yield, and that is simply the amount of product expected from a given amount of reactant based on the coefficients in a balanced equation. So the theoretical yield is the number you get from your calculator. So when you do the conversions that we did above, and the number that you get at the end from your calculator, that is the expected amount that you should get from that equation. On the other hand, we have the actual yield. So here this statement says, usually, however, the amount of product formed is less. And we talked about why it's less, usually because of human error. We make mistakes in the lab, we spill things, and so on. And so we typically don't get 100%. The other word in the equation is the actual yield, and it's just as it sounds. It's what you actually were able to isolate from the reaction. So if this were a lab situation and at the end of the experiment you would take the mass of your sample, that would be your actual yield. And so we can work through a problem here. It says, in the reaction of ethylene with water to form ethanol, this has a calculated theoretical yield of 23 grams of ethanol. What is the percent yield if only 15 grams of ethanol was actually formed? And so we can set up our equation. So percent yield is equal to actual yield, and our actual yield was 15 grams, divided by the theoretical yield, which was 23 grams. And since we want a percent, we want to multiply by 100%. And we get a percent yield of 65%. All right, let's move on to something called limiting reactants. The limiting reactant is the reactant that will completely be used up in an equation. And so just as an example, they have pictures of bread and some kind of lunch meat, it looks like. And so we know that when we are making a sandwich, we need 2 pieces of bread and typically 1 piece of lunch meat. And so if we look at our ingredients here, I'm counting 1, 2, 3, 4, 5, 6, 7, 8 pieces of bread. And we have 3 pieces of lunch meat. And if we were to make sandwiches, we can see that we can only make 3 sandwiches because we only have 3 pieces of lunch meat. And we were going to have 2 pieces of bread left over, 2 pieces of bread that we see here. So in this example, our lunch meat was our limiting reactant. It's the reactant that was used up first. And as soon as our lunch meat ran out, we could not make any more sandwiches. So similar to that, in a chemical equation, we can have a limiting reactant, and as soon as the limiting reactant runs out, the reaction stops. and so it is important to know what that limiting reactant is. So here's a problem. It says determine the limiting reactant for the following equation if you start with 4 moles of H2 and 3 moles of O2. And so our first order of business then would be to write out the conversion factors that relate the moles of our reactants. And so according to this chemical equation, we're looking at H2 and O2. We see that we have 2 mole of H2 for every 1 mole of O2. We could also do this for molecules. I'll just continue to use moles here. And so we want to choose the correct conversion factor that's going to allow us to cancel out, I'm going to say moles here, of H2. And so we can see in the conversion factor that I have just written, O2 is on the bottom. So we need the other conversion factor. So we're going to put O2 on top so that we have H2 on the bottom. And that would be our conversion factor that we would use. All right, so it says, again, determine the limiting reactant. We have 4 moles of H2 and 3 moles of O2. All right, once we found our conversion factors, then it's just a matter of looking to see which one's going to run out first. So we can set up a problem, again, to relate molecules of H2 and molecules of O2. And so we're going to start with the 4 moles of H2. So 4 mole H2. And we're going to use that conversion factor that we found earlier. It says 1 mole of O2 is equal to 2 moles of H2. And remember, this came directly from our balanced chemical equation. And so when we do the math, 4 divided by 2 equals 2 moles of O2. So we set it up this way so that moles of H2 cancel. And so in order to use up our 4 moles of H2, we would need exactly 2 moles of O2. And so we want to take a look at what we have here. So there's 2 possible outcomes. So if the amount present of the second reactant is less than what is needed, the second reactant is the limiting reagent. But if the amount present of the second reactant is greater than what you needed, then the second reaction is in excess. And so when we take a look at that, it says in this reaction, only 2 molecules of O2 are needed, or 2 moles of O2 are needed, but we actually started with 3 moles of O2. So from this, we can see that O2 is going to be in excess. We have more than we need. So that means that H2 is our limiting reactant. So hopefully that makes sense. Using our conversion factors again to find out exactly how much is going to be needed. If we start with 4 moles of H2 and convert that to O2, we can see that we only need 2 moles when in fact we had 3 moles available to us. We could have just as easily started with 3 moles of O2. This time we would need the conversion factor that has O2 on the bottom, H2 on top. We set it up this way so that we find out how much H2, so 3 times 2 is 6 mole of H2 are needed to completely react with 3 moles of O2. But notice we only have 4. So this again lets us know that H2 is our limiting reactant, which is the same conclusion that we came to using the other method. All right, let's look at our next problem. So we have this balanced equation. It says determine the limiting reactant when 10 grams of N2 react with 10 grams of O2. So it gives us the molar masses here. And we can see that the first step we need to do is to convert our grams to moles. We have to convert grams to moles because the equation is written in terms of moles. So the first step is always going to be convert grams to moles. So let's start with N2. We have 10 grams of N2, and we want to convert that to moles. And so we know that 1 mole is equal to 28.02 grams. And so we can do the math and see, as grams cancel, we would have 0.357 mole of N2. We'd want to do the same for oxygen. We have 10 grams of oxygen gas. 1 mole is equal to 32 grams. Grams cancel, and that gives us 0.313 mole of O2. All right, so now that we've changed both of our substances to moles, we can identify, or we can use nitrogen. We can start by using nitrogen, and we're going to use our moles that we have. And so we started our equation here with 0.357 moles. We use our balanced equation to get our mole to mole ratio, and that is simply 1 to 1. And so we can see that we need 0.357 moles of O2. Then we look back to see how much we started with. The amount of O2 that we started with was 0.3313, which is less than the amount that we need. So therefore, oxygen is our limiting reactant. Remember, the limiting reactant is the one that is going to run out first. And so we could use the amount of oxygen that we have to solve for how much product that could be formed. So limiting reactant is a very helpful tool that you would need to learn so that you can determine how much products can be formed. All right, that is it for part 2 of Unit 5. I just want to encourage you to practice, practice, practice. There's a lot of skills here that you need to become comfortable with that we will use throughout chemistry. All right.